classes were canceled or something. But okay, anyway. So today, we'll continue talking Bootstrap, this time with library boot, okay? So you don't need this to do your homework, but a lot of times when you do Bootstrap, or if you read someone else's paper, or even when you read our own textbook, they will use this library boot to conduct the Bootstrap, okay? And this package has been around in R for a very long time. It's updated with every update of R. Every time R gets updated, they update this package. It's very used frequently. Okay, so we're going to revisit our data set, okay? And again, we're looking at education achievement numbers from students or from immigrants from Latin American countries, and in particular, we are interested is there a difference between students that immigrated from Mexico versus students that immigrated from other countries, okay, other Latin American countries, and so this is what we're looking at, okay, and this is what we did. Just for the sake of what I'm going to be doing later, I've chosen to arrange the data set, okay, by this variable Mexico, or came from Mexico. And so, the head, it will be people who immigrated from Mexico, and tail will be people who immigrated from countries other than Mexico. And these are our summary statistics. This is what we observed, and we said that the observed difference as far as education achievement levels, at least in this sample of 150 people, the difference is 5.92. And the question was, could this have been a result of random chance? And so for the non-parametric bootstrap, we said, under the null hypothesis, both groups, if the null hypothesis were true, the numbers that came, the numbers for the immigrants from Mexico and the numbers for the immigrants from other countries come from the same population, right? So I just take, and the population, we can just use our current 150 values of achievement levels for that. Yes, question?
In this case, you the mean of group A minus group B, right?
Yes.
So, but on the observation difference, like is it group B minus group A? Does it matter?
Oh, you are correct. I did group B minus group A. I did the group of 34 minus the group of 116. It's a good catch. Later on, because I do the absolute value, it's okay. But you're right. It normally it normally would matter, right? If you have, especially if we're doing something like more extreme. So if it's negative, it's going to be negative or something more negative. So. I'm sorry?
We should be consistent for...
Yes. So you should be consistent in your thing, and that's a good catch. I didn't notice because we've been doing the absolute values, but yes. So yeah, it would be the group of 34 minus the group of 116. But again, because I'm doing the absolute values, it works out okay. But yeah, you should stay consistent in your thing. So that's a good catch there. Okay, but yeah, under the null hypothesis, we're saying the 116 values in group A come from this population, and the 34 values in group B come from the same population. And in our case, the population is just this column of 150 values, infinitely replicated, or just sampled with replacement. Okay. And this time when I ran it, I got an empirical p-value of 0.0392, which it's a little different from what we got last time, 0.0465 or something, but still, within reason here. Okay. And okay, so that's kind of our recap from of what we did on Wednesday. All right. And so today we're gonna look at package boot, which is going to do a lot of the same stuff, and but again, I didn't finish all of my slides, so we're gonna have to wing the last bit. Okay. Okay. So yeah, if you do Bootstrap, probably it's good to learn this, okay? Learn library and package boot. Again, it's not required for your homework, but if you want to use this for your homework, you're welcome to do so as well, all right? And you just call library boot, all right? This is probably already installed on your computer, but I don't know, maybe not. Okay, so you just call library boot. All right, and so if you call help on boot, all right, it comes with a bunch of stuff. And a nice thing here is if you've got a Mac, and I think maybe we can do it on a PC also. I don't know. There's this option called Parallel, which will use the different cores on your computer. So if you wanted to do like a bajillion bootstrap replicates, you can parallelize the process just by turning on Parallel into one of these things. I think it works best for a Mac. The multi-threading stuff on a PC is done a little bit differently, whereas on Unix-based machines, it's already part of the OS. Okay, anyway, this I just copied straight from the help when you call for help on boot, and it does it. You know, you can both do parametric and non-parametric ones. We're going to look at the non-parametric, all right? And you can see when you use the thing, the three most important arguments are data, statistic, and R. Okay? Everything else comes with its own default levels. Sim, ordinary, S-type, strata, L, M, weights, rand generator, D, whatever. Things like this, okay? MLE, simple, parallel, stuff like that, okay? So the three arguments you have to provide are data, statistic, and R, okay? And so this is what help says for data, statistic, and R, okay? So data is a vector matrix or data frame. So probably a data frame, right, is most of your data scenarios. But yeah, you can do a vector matrix, right? And says if it's a matrix or data frame, each row is going to be considered as an observation. So in tidy form, right? Each row being an observation. And as far as the statistic goes, the statistic is a function, okay? And it says a function which, when applied to data, returns a vector containing the statistic or statistics of interest, okay? If sim is equal to parametric, then the first argument to statistic must be the data. For each replicate, a simulated data set returned by randgen will be passed. In all other cases, okay, statistic must take at least two arguments, all right? And this is going to be what we have. The first argument passed will always be the original data, and the second will be a vector of indices, frequencies, or weights which define the bootstrap sample, okay? Further, if predictions are required, then a third argument is required, which would be a vector of the random indices used to generate the bootstrap predictions, okay? Any further arguments can be passed to statistic through the ... argument. Okay, so we're going to look at this case where the first argument is the data and the second argument is the indices. But you know, it also says you can do bootstrapping where you're going to be making predictions and such, and that can also be done. Okay, and then R is going to be the number of bootstrap replicates, right? So just in summary, the three arguments we provide will be the data. The second will be the statistic to be calculated, which is a function that we define. And then the third is the number of replicates R, right? And we can specify other arguments, but they all have default values, and most of the time the default values are just fine. Okay, so one thing to note is that when you use boot, it resamples the indices, okay? So again, the idea of bootstrap is that our data is representative of the population, and so I can take my current sample of data and I can kind of clone it a whole bunch of times, and I'm going to say this looks like my population, all right? And we can achieve this without actually needing to do the cloning of the data by just resampling our data using sampling with replacement, okay? So I can just resample my data, sampling with replacement. And the way boot achieves this is it samples with replacement using the indices, okay? So it's going to resample only the indices, not the actual values, And then once it does that, it subsets the data based on the resampled indices. Okay, and so I'm going to just show just some code, not using boot, but just some code showing this idea. Okay, so this was the original code that we ran. Okay, which is basically here is my data, and this is the vector of 150 values, and I'm sampling it with replacement, and I'm drawing a sample of 116 into group A, and I sample with replacement, drawing a sample of 34, throwing that into group B. I calculate the difference between the mean of group A and the mean of group B, and I store that into this vector differences. Okay, so that's what the regular old non-parametric bootstrap looks like. Okay, I could do something similar, all right, and then if I calculate the p-value, calling the absolute value of the differences, how many of these are greater than our observed difference, we get 0.0392. Okay, if I want to resample the indices, this can be done, all right, and I just want you to pay attention to basically what is similar between this block of code and this block of code. Okay, so here, inside my loop is I create this vector called resampled indices. Okay, resampled indices, I take the numbers 1 through 150 and I resample 150 of them with replacement. Okay, and so what that means is I'm going to get a vector of length 150 where some of these numbers, where all the numbers are going to be between 1 and 150, but some of those numbers will appear more than once and some will not appear at all. Right? It's kind of because that's what happens when you resample, sample with the replacement, right? Like if you roll a die 6 times, you might get one of the faces show up more than once and one of the faces not show up at all and things like that. Okay, so I get resampled indices, and then I subset the data set Latino using those resampled indices. Okay, so this is our data frame name. And putting in resampled indices, comma, this is going to give me back basically those rows. Okay, so this is going to be my resampled data. Is that all right? And then I take resampled data $achieve, and I pull out the first 116 values, and then I do resampled data $achieve for the last 34 values, and that's going to be group A and group B, and then I calculate the difference between means. Is that okay? So I guess conceptually, can we see how the results of this and the results of this are pretty much the same? All right. And oh, why didn't the empirical p-value print out? What is going on with my screen? Oh, eval false. I didn't want that. Okay, so let's actually, what is happening? That's weird. Okay. Okay, anyway, when I do the empirical p-value here, we're going to get the same thing, 0.0392 it should be. Let's see. I guess Bootstrap is a little bit heavy on your computer. Okay, so conceptually, these ideas of resampling the values directly and then resampling the indices and then subsetting according to your resampled indices, those effectively are the same. Can you render this, please? Okay, there we go. So the original, we resampled the values directly, we resampled the indices and subset, and we get the same value here also. Okay, so that's neat. Okay, so if we want to use library boot, we're going to write a function to allow boot to basically do this. It's going to resample the indices. All right. So so this statistic function that we're going to write takes in 2 arguments. One is going to be the data, and one's going to be the indices. And then the function boot performs the resampling of indices itself and passes the resampled indices as an argument in the function. So inside our function, we don't need to do the sample operation. Boot is going to do that for us, all right? And so again, in our case, we wish to calculate the difference between the mean education achievement of the immigrants from Mexico versus the immigrants from the other Latin American countries, and we're going to take a look at this, right? So this is what our difference function might look like, okay? So our function, so look at this. This is where I've resampled the indices. I subset the data, called my resampled data, and from here I pull out the first 116 values and give it to group A, and then the last 34 values and put that into group B, okay? When I do the function, okay, so this is a function I can now use with the function boot. I pretty much do the same thing, except notice our function, so before I just had a loop that I wrote in the global environment, okay? This is now a function, so there's no loop here, but the function takes in the data and the index, okay? So when I call the function, it's gonna be basically like function Latino data set, data is equal to Latino, and index will be basically a sample of 150 values or something, right? And then so I subset the data using these indices that are passed, okay? So you take the argument data, take the argument index, and I subset that and I call that my resampled data, all right? Then I call resampled data $achieve, pull out the first 116 values, resampled data $achieve, pull out the last 34 values, and then I calculate the difference between the mean of group A and the mean of group B, okay? And this is the value that gets returned. I don't need to assign it anywhere in here because this is a function. It's whereas before it was not a function, it was a loop that I ran in the global environment, so I had to assign it to that object differences and stuff. But here, this is just the value that the function returns, okay? And so boot is going to call this function repeatedly, like 10,000 times or however many times I say R is, and it's going to call this repeatedly, and it's going to, whatever this returns, it's going to store somewhere. Boot is going to store it for us, all right? So I guess I wrote all of this code hoping that you can see, hoping that you understand this from Wednesday, see how we can transition from this to this, okay? And then how we can transition from this loop that we're writing in the global environment to a function that I can then use in boot, okay? And so there's this and this are similar, and the idea is that this thing and this thing are also similar, because if you're going to use boot, you've got to write functions like this, and this is how we would structure our function here. Okay, and then so calling boot is simple, all right? I just run boot, and I say data is equal to our data from Latino. The statistic is this difference function that I wrote on the previous slide, and I'm going to do 10,000 replications. Okay, and I'm going to store all of this in boot underscore results. Okay, and that's it. All right, and so the result of boot underscore results looks like this, okay? And pretty much the most important things are going to be T0 and T, okay? T is if you run this function, diff function, on the data set, it gives us back a difference of negative 5.92, right? So this is the difference between the observed difference in our data, okay? Now, and this is why I had to, at the very, very beginning, I sorted my data frame. I sorted based on that column Mexico. Did the immigrant come from Mexico or not? I sorted there so that the first 116 values would be immigrants from Mexico, and the last 34 would be immigrants from other Latin American countries, okay? And that way, when I calculate this statistic, which says take the first 116 values and put them into group A, and take the remaining 34 values and put them into group B, it's going to produce, you know, our observed difference here, okay? Now, if we didn't do that, this value would be off, okay? This thing, the $T, is effectively the same as storing all of the differences as we ran that loop, right? So back here, when I stored all of these differences between group A and group B, I stored them into differences. This vector here, $T, is going to be basically equivalent to that. It's technically a matrix. It's a matrix with 10,000 rows and 1 column, okay? And boot, the function boot, when you write this function, here we just have it return 1 value, but technically we could have it return a vector of values, right? So I could say, you know what, I want the difference between group A and group B. I also want to look at the standard deviation of this thing. I also want to look at, I don't know, the correlation of something, right? So you can actually calculate, have the function return a vector of values, and it's going to store all of them into this matrix T. And if you return a vector of 3 values, then T will be a matrix with 10,000 rows and 3 columns, 1 for each of the values that your vector returns. Okay, which is pretty neat. Yeah.
So when you say data organized or like arranged by descending order of like the status, if you're going to resample it, what's the point of like arranging it?
Yeah, just so that we're able to calculate this quote baseline statistic. Okay, so we had that observed difference of negative 5.92, right? And so boot will calculate T0. T0 is basically when you call the difference function, for the index, normally we say resample the values 1 through 150 with replacement, okay? But here, if I just provide index 1 colon 150, so I'm not actually resampling, I'm just providing the vector 1 through 150, or the values in order, that's what T0 would be. It would be, what is the value of this function statistic for kind of the original data set, okay? And so here I'm just saying take the first 116 values, call that group A, and the last 34 values and call that group B. And that will provide the difference between the two different groups, okay? You know, otherwise this value T0 will not be relevant to our data, okay? Which I guess is fine, but it's more useful if it is relevant to the data that you're looking at, okay? And then the other things that come as results.boot, and maybe I'll just load this up. Can I zoom in here? Kind of. Nope, wait. Do you know how to open this in your browser? Okay. Well, basically, these are the other things oh wait, this is bootstrap confidence intervals. Here, let's go to, oh, here it is, boot. All right, so this is these are the things it returns. Okay, so T0 and T are probably the 2 most important things, and then R is everything else is pretty much information about the bootstrap that was performed. So it's going to tell you like how many replications it did. It also keeps like the entire data stored in there. It tells you the random seed that got used, which is different. So when you do set seed with boot, your answers will be very different from what happens when you just run it yourself. Okay, and it gives you basically the function that you used and all of this stuff. So it's just kind of like you can package this up and see exactly the call that was done. Okay. Okay, and so here, if we wanted to calculate our empirical p-value, we can just take the results $t, which is basically my vector. I can call the absolute value on that and say how many of those are greater than or equal to our observed difference, and we get 0.0485. All right, and you know, we see some variation in this, okay, but you know, we're getting something, you know, at least in the range that makes sense. So this is what we're getting here. So the reason why people like to use the function boot is it comes with certain functions and methods that already exist. So one of them is it comes with its own plot method, okay? And so here, if you just do plot on the results that you calculated, right? So remember back here, all I did is I called boot and I stored the results in boot results, right? So if you call plot on boot results, it produces this this plot here. Just go ahead and run that. Jeez. What is going on? I don't know. Okay. All right, so, this is basically you get a histogram of the different values of t. In our case, looks very normal, and it plots this dotted line right at your t0, okay, which is at negative 5.92, and you get a sense of how often you get a value more extreme than what you get, okay? And here, this is a QQ plot, and it for whatever reason, it's not, I gotta reshape this thing, okay? And we can see the distribution looks very normal, right? So it's a quick way to check these things. Here we can just plot the, I can call density on this and plot the density, and we get something that looks a lot like the normal distribution, which is a good sign for us, okay? And then, okay, so this all got chopped up again. If I minimize, okay, so now you can also look at boot.ci. This will create confidence intervals based on your bootstrap results. And so this will kind of give you like a 95% confidence interval for the bootstrap. Now you get different things. You get normal, basic, and BCA, which I always forget what the difference is between all of these things. So I looked up bootstrap in R, and it here it gives us, so this is I guess I'll link to this tutorial, okay? But it talks about some of the differences between exactly what these confidence intervals are, okay? So so here the percentile confidence interval, okay, which would be right? Okay, so the where did it go? Okay, so the percentile confidence interval is this, okay? And what that means, and sorry, I didn't finish my slides here, is basically, this is the results of all the t's, okay? And we're looking for the middle 95%. So it's like I take this vector, okay? Take this vector of all these values and I sort them from biggest to smallest, okay? And I think I've got 10,000 of these, and I want the middle 95%. I want the middle 9,500, okay, out of 10,000. So that means I'm going to look basically at the 2,500th, right? If I sort these from least to greatest, I would look at the 2,500th, or 250th, sorry. I want the middle 9,500. Okay, so I would take the 250th, and then I would take the 9,750th. Okay, so I would basically throw away the top 250 and the bottom 250, and so the middle 95% goes from around right here to around right here, and that's what I get. So my percentile confidence interval goes from around negative 5.9 to positive 5.88. Okay, the other confidence intervals, okay, will be the normal confidence interval, which will take your T0 statistic, okay, which we found to be negative 5.9, okay, takes that, and then it basically does a plus or minus 2 standard errors, okay, or 1.96, two standard errors, and so that produces, so it's, why is this, okay, I'm confusing myself here. I would expect it to be centered at negative. All right. Let me look up what's going on here. Okay. We go up or down two standard errors for the normal confidence interval. The basic CI is does this, and basically it takes double your T0 statistic, again, the value you calculate for your baseline data, and then it subtracts off or adds the basically your 997.5 percentile and 2.5 percentile, okay? And then the BCA, I have no idea what this is. It's another confidence interval. Bias corrected accelerated. So I didn't learn this, but let me see. The formula for it is not very complicated, but somewhat unintuitive, so I'll skip it. Well, thanks a lot. Okay. See article by Thomas DiCiccio and Bradley Efron. If you're interested in the details, acceleration mentioned in method's name requires using specific percentiles of bootstrap realizations. Sometimes it may happen that these would be some extreme percentiles, possibly outliers. BCA may be unstable in such cases. Let's look at BC alpha CI for petal width median. Okay. All right. I still don't know what that means. But apparently it's useful enough that they decided to include it in this confidence interval thing that you get when you call boot boot.ci. I think frequently people use the percentile one, and I'll have to see why I'm getting such weird results over here for normal and basic. But that's what we're getting here. Let's see. Bootstrap variances needed for studentized intervals, extreme order statistics used as endpoints. Okay, I don't know. I have a confession. I don't often use Bootstrap myself for, I don't use this package very often, other than teaching it in this thing. Just because I see it a lot in the literature, okay? Like I see it used frequently on, I don't know, papers that people write. So I feel like it's important that I cover, but I don't actually use it myself very often. So anyway, I'm probably not the expert. Well, I'm definitely not probably not. But this package boot comes with a lot of other stuff, right? Like if you look at the help file is 117 pages long, okay? And it does all sorts of stuff. And I'm just looking only basically at the original boot function. There is another function that is very useful, cv.glm. I need a sip of water here. cv.glm, and that's actually very useful to perform cross-validation, which is not covered in our course. I cover it in 102B, so we'll take a look at it but there's other stuff, and if you're interested in this, you can look up something also called the jackknife. Okay, the jackknife is a technique that has actually been around before the Bootstrap, and it's used to give you a sense of the amount of variation that exists. Okay, so you can read about it on Wikipedia, and the notion for the jackknife is that you take your data set, you remove one of them, calculate your statistic on it, and you do this again and again. So each time removing one of these things and seeing how much variation there is between each of the different values. And I think that's also implemented in boot. But again, I'm not 100%. Yeah, here it is. Jack after boot. Jackknife after bootstrap plots something. Looks like I can just call Jack after boot. Let's see. I don't know what's going to happen. Let's just see it, okay? Okay, Jack after boot on my boot results. Let's see. Is this even... Ooh, okay. Never mind. I don't know what this means. Okay. I feel like I did something wrong. Okay, I don't know. I have no idea what that means. 5, 10, 16, 50, 84, 90, 95 percentiles of T star. Okay. Well, I guess. All right. Anyway, just delete the last 15 minutes of the lecture, okay? The important part is this thing, all right? Is that if you want to use boot, and it's a decent package, okay? If you want to use boot and take advantage of its abilities, you have to be able to write a function like this, okay? And to write the function like this, you have to be comfortable with the idea of resampling the indices rather than the values directly, okay? And the advantage is you can have it produce a vector of statistics, and it'll keep track of all of these for you, okay? So take a look at, this is what we did basically on Wednesday, and then here I rewrite it to resample indices, and then you rewrite it to make it a function that resamples indices, and this is the key part. And then using the boot function or the boot package, yeah, I'm sorry, it's not something that I would consider that I'm an expert at. I just know that it exists, and a lot of people do use it, and so I felt like it's something you should at least have some familiarity with, so I want to introduce that here. Okay, we'll call it a day here, and have a good weekend. Stay safe, you guys, and we'll see you guys maybe on Monday or wherever. Thanks for tuning in. If you're watching at home, I hope everybody is watching this at home.